So, today I will demonstrate basically the verification of Dulong-Petit law. Verification of Dulong-Petit law. Okay. What is that? The heat capacity of a mole of many solid elements is about 3 R, where R is the universal gas constant. It is just like Ohm's law, where current and voltage are proportional. Okay. So, similarly, in case of heat, so this is the another law, Dulong-Petit law. It tells that the for any metal, most of the metal, elemental metal, okay, for most of the metal, elemental metal, its heat capacity, molar heat capacity basically, heat capacity of a mole is 3 R. R is the universal gas constant. Its value is around 2 calorie per Kelvin. Okay, 2 calorie per Kelvin per mole, of course. So, it's this value R will be around 6 calorie, not R, heat capacity, molar heat capacity will be around 6 calorie per Kelvin per mole, of course, that will be there. So, this is the experiment today I will demonstrate. It is a very easy experiment. Okay, its working principle formula is very simple. So, working formula I have written. These are basically from the principle of calorimetry. Okay. So, what is the principle of calorimetry? Heat lost by the hot body equal to the heat lost by the cold body when they touch each other. When they touch each other, when they are in contact, one is hot body and another is cold body. So, one will lose heat and another will gain heat, and then they will come in a equilibrium temperature. They will come at a equilibrium temperature. So, this arrangement is done, wherever it is done it is called calorimeter. It is done calorimeter, right? It is done calorimeter. So, now if I take so here as I told, for metal, solid metal, we want to verify this law. So, that means I have to find out the molar heat capacity of the metal. So, if I take metal, say here metal, 3 pieces of same metal I have taken, 3 pieces of same metal I have taken. So, mass of this metal is say m. Here in this formula it is m, and its molar heat capacity is C, molar heat capacity is C. Okay. And now its temperature is T2, and when it will, so when if it is say hot body, it is hot body, I have to make it hot. So, its temperature T2. Now, if I put it in a cold body, generally we will put in a water in calorimeter. Okay. So, in calorimeter, water as well as this copper container will be there, and they are sealed in a thermal radiation, so that there should not be any loss of this I think I have to, it's boiling. Let me switch up this one, because okay. So So, in calorimeter, whatever the equilibrium temperature T equilibrium, so MC T2 minus T1, so that is the change of heat of this hot body equal to, now in calorimeter as I told, water and this container is there. So, this is the mass of water and this we have written W is the water equivalent of the container, okay, is the water mass equivalent of the container, okay. So, that I will show you. See, this is not mass into the specific heat basically of that material. So, that is the water equivalent we tell. So, that is W. So, this is the total, so you can say, mass of the container and the water. So, this now its temperature was initially say T1, now it is increased to T equivalent. So, difference of this temperature. So, this the this amount of heat is gained by this water and container, and this amount of heat lost by this hot body. Okay. So, this is the working principle of this work. So, what I need to do? So, I need to do this, I have to take metal. So, this I have taken metal, okay. I have to find out the specific heat, molar specific heat of this metal. Now, I have to heat it, okay. I have to take at higher temperature, I have to make it hot body. So, here you see water is boiled, just I kept it in boiling condition, because then we will lose time or will not lose time. So, this is the thermocouple is put in the, so this is the heater. On this heater I put water in a container, I took water, this power is given from there to the heater and then its water is boiled, now it is boiling. So, I think 10-15 minutes back I just switch on this one, now I switched off this one. So, this thermocouple is there. So, this here we are getting the reading of the temperature from this thermocouple. So, this is the, I think this is the yes, this thermometer is of thermocouple type. So, so here this reading of this water, temperature of this water is 97.8, is decreasing. So, I think I will switch on this one, okay, now. So, so this type of metal, already another metal I put it here, you see, here I think is the aluminium, okay. So, yeah, this is the aluminum metal, okay. So, already I have put here. So, it is a hot, its temperature is this one, okay. So, so now this hot body, now what I have to do? So, this mass I have to take. So, that will take, we have balance. So, we will measure the mass of this hot body. So, before putting there, I should take mass. Okay. So, it is showing this 178.5 gram, 178.5 gram this one. So, we will do this experiment for 3 metal. So, one is aluminum there, one is, this is iron basically, okay. It is the iron, this metal is iron, and this metal is brass basically. Here another sets of material I have taken, okay. So, this is the copper zinc alloy. So, it is brass basically, okay. So, so similar way you should take mass and note down the mass of the metal. So, now you can ask me this, why we have taken 3 pieces, why not 1 pieces? So, you see 1 pieces means it will be bigger one, okay. So, then to get uniform heat of this bigger one, inside heat has to go inside, you know. So, it may not, this metal, this temperature, that may not be uniform in this in single piece. Okay. So, if we take small piece, so you can make sure that okay, the temperature throughout this material is uniform. So, that is why we have taken 3 pieces, okay, instead of 1 pieces. So, mass of this metal, 3 pieces, 3 types of metal we have taken, mass of the 3 types of metal we have taken. Now, here we have to take mass of water and mass of this container, okay, calorimeter. So, this is the basically calorimeter. This is a copper container calorimeter, okay. So, and this is the stirrer. So, to get the uniform temperature, so we will use this stirrer. So, with this stirrer, so we will take this weight of this, okay. This is the 91.1 gram, and the specific heat of this copper material is will be given, is supplied, is known. So, I will multiply with this this mass into this specific heat of this copper. So, that is basically W, whatever the formula I have shown you, that is the water equivalent, we tell water equivalent. So, this is W, and this MW is the mass of water, okay. So, here I will take mass, I will take water. So, I have water here, I think this is the dirty water, I need clean water. So, I think just I can put some water this way from this bucket, okay. So, put some water, okay. I put some water, okay. Now, again container plus this water, so it is a 312.1 gram, okay. So, minus this earlier reading for container we have taken. So, then we will get the mass of water only, okay. So, all this reading you should note down. Now, I will put this one in thermal insulator, you know, I will put this one in thermal insulator, I will put this one in thermal insulator, I put thermal insulator, fine. And I have one, so here I need, so I have to seal as much as possible. So, I think this way stirrer I can use, okay. How to put, I have to see stirrer. Can you tell me this stirrer, how I will take this stirrer from here?
Yes.
Huh? Through this?
Yeah.
Okay. Because I used the another setup, yeah. So that's why. Yes, okay, fine. So, the stirrer, this other end of the stirrer I have taken out, and this I need to measure the temperature of the thermometer. So, for that I will use this, okay, thermometer. This is the mercury thermometer. It's the opposite side, yes. Okay. Okay. Then I will just keep in a position that is a thermal, as much as possible we have to seal thermally this, okay. So, now it's I have to note down the initial temperature of this cold body. Now, this is the cold body, water and the container is cold body. I have to note down this temperature. Now, I will feel difficulties to take reading, okay. I can see it is 20, 20, yes, 22. This temperature of the water, I can see this is the 22. Yes, so one should use this, then it's easy to take reading. Yes. Yes, it is 22. It's 22. Is that 22? And I have to note down the least count of this thermometer, that is 1 degree. Okay. So, now I have hot body now, hot body. So, this temperature is 90, I have to note down this is 99.0, 99.0. Then I should take it slightly close to it, okay. And then just quickly I should put this mass into this, okay. I should put this mass into this. I think I will take this way, then I will take this mass out and very quickly I have to put it, okay. Very quickly I have to put in and then just put this way, yes, okay. So, take away slightly here, I will keep it, okay. Okay. So, now you see hot body and cold body are together in a calorimeter. Now, just I will start it. So, why? Because this hot body is in contact with water. So, that water close to the hot body, that is hotter, that will be the temperature will increase, but other area this water the temperature will be different. So, here we have to start it so that temperature of this cold water is uniformly increased, okay, taking the heat energy from the hot body. Okay, so that's why we need to stir it. Okay, so I think it's continuously one should stir it. Okay, and then also I would like to see the temperature and whether it is coming towards steady. So I can see now temperature is 32. Now I can see temperature is 32. So from 22 it has come is 32. I think in camera it's maybe slightly difficult to see. Camera maybe, but I don't know whether you can see in camera this reading. Okay. So sometimes I have to, and in the meantime I can put another piece of hinge to heat it. Okay. So because to come in equilibrium temperature it will take some time. So I will not repeat the experiment. So this way, when one you are using for measurement, other one you just put for heating. Okay. So but I think this just one has to repeat, but this one let me just stop it, because I will not repeat the experiment. Just I showed you how to repeat the experiment. So this in the meantime, when this will complete, then I will use the second one. But again I have to throw this water, take fresh water, and measurement, everything you have to repeat for another metal. Okay. So let me, I think I should do this. So what is the reading? Let me see. It is almost steady. It is this. It is a 30. I can see it is 32 to 33. I can take this reading as a 33, and for longer time it is 33. Okay. So it depends, equilibrium temperature you will get 33 or 43. It depends what is the quantity of your water, because I have taken more water, it seems. Okay. So that's why this equilibrium temperature it is 33. So it is in equilibrium, but I should check. I should take at least 3 readings to check whether it is in same, it is giving same reading or not. Let me check it. I think I have to rotate and yes, it is in same position 33. It is in same position 33. So taking reading from the thermometer is not difficult one. So you can take. So now fine. Okay. So I will note down this is T equilibrium, TEQ, whatever I showed. This is the temperature. I have to note down. This temperature. Okay. What is this? Another part I have. Okay. So so this, as I told, this for 3 metal we will do experiments. So presently we are doing for aluminum. Okay. Now mass of the metal I noted, I 91.2 probably. Yeah, I have to write this one, and then temperature T2 as 99, temperature T2, this I have noted down. This temperature T1, so that was 22, that I have to write, and then mass of water in gram, mass of water I have, so mass of the metal, this is the mass of water. So that I have to write, because every time I am changing the water, right, for 331. So I am changing this one, I am changing the metal. Okay. So that's why I have taken in table, because with this, so these two will change. So, but other mass of the container, water equivalent of the container is the remain same. Okay. So then I should, yeah, then finally I should note down this T equivalent. Okay. Then I should note down T equivalent. So now using the formula, one can calculate the C. One can calculate the C, because I have all reading is in my hand. And as I told, I will tell what is water equivalent. Mass of calorimetry with stirrers, this mass of copper, basically this is the mass of copper, that is equal to this 129.7 gram, 7 gram. So this is for another container, this data is for another container. We have bigger container, this smaller container. In our case, is a 91.2. You should write 91.2. This reading I have written for another container. I think I have bigger containers. Here I have bigger containers. So that, yes. So this one I have bigger containers. So this mass of this one is 129.7 gram, but now I am not using this one, I am using the smaller one. So that is 91.2 gram, and the specific heat of copper is known, this given, this one. Okay. So now if you, so water equivalent of calorimeter with stirrer is basically W, whatever is formula we have written. So that W equal to, I have to multiply this with the mass, but not for this mass. If mass is this, then it will be this value. Okay, 1.1. But in our case, present case, one has to find out. So this is the water equivalent. How to calculate water equivalent? This. Okay, and as I told, least count of the digital balance you have to write. This is 0.1 gram, and least count of the digital thermometer. Digital thermometer, this is a 0.1 gram. Least count of this for T1 we are measuring this one, no? T1 and T equivalent. So this one least count is 1 degree, okay, not 0.1 degree. So 1 degree, that we have to note down. Okay. So then just all data is available. You calculate this specific, and calculate the heat capacity, molar heat capacity for these two metals, and see this these 3 metals will give more or less same value of it is close to 3R. If so, if these 3 gives the same value, approximately same value, then you can conclude that Dulong-Petit law is verified, and that value should be equal to around 6 calorie per Kelvin per mole. Okay. So this is the experiment, very simple experiment, but very interesting. This is a law. It's this heat capacity, molar heat capacity is independent of material. This is the beauty of this law. Okay. So that's why this simple process way one can verify this law, which is Dulong-Petit law. So I will stop here. Thank you for your attention.